Let's do one more optimization problem of level 2. Remember, level 2 I denoted those which are a little bit more complicated, and this one is probably on the highest level which we will study in this calculus class. So it doesn't get more complicated than this one, but this one does have some twists to it. So let's remind ourselves of our saying for the optimization. U draw names for max and min. U is understand, meaning identify known and unknown quantities. Draw is a sketch, and here we will see that the sketch is actually very important to understand the problem. We give names to variables, we identify formulas and simplify, and then we use our max and min methods as we have learned them. So here's a problem. We have an island which has particularly good feeding grounds for a bird, and the bird has to fly over the water to its nest site, which is over here. But now the flight over water is very costly energy-wise. It is much more tiring to fly over water than it would be to fly over land. So the bird has several options. So it can do the gray route, it can fly the shortest distance to the land and then cross over to the nest site. But then in total it has a long distance to fly. Another alternative would be the orange route, so to fly directly to the nest just over water. But of course, then they would use lots of energy to do this. And an intermediate solution would be the red one, where the bird flies somewhere to the shore and then flies a piece along the shore to the nest site. So the question is there an optimal point C, kind of halfway between point B and point D, which would minimize the energy? So the text here summarizes all this. So let's look at a few of the details. So consider a bird that has to go back and forth between an island at C, located 5 kilometers from the nearest point B. And its nesting area D is 13 kilometers from the point B along the straight shore. So this is a 13 here and this is a 5 here. We assume the flight over water takes 1.4 times more energy than the flight over land. So what is the path of the bird with the lowest energy? First step was to understand the problem, see what we got. So we know the distance from the island to the shore, 5 kilometers. We know the distance from the point B to the point D where the nest is, which is 13 kilometers. We also know the water travel takes 1.4 times more energy than the land travel. Unknown, however, is a point C. So let me introduce another color. So the point C here is unknown. We don't know where it is. And unknown is the energy which we use. The sketch is done, but here in this case the sketch is actually rather important. So then we introduce names. So we have the point A for the island. Let's call this A. B is the landing point right here. C is the intermediate point which we are looking for. D is the nest site sitting right here. And then I introduce another variable which I call x as the unknown distance from B to C. Right, from the distance B to C or the distance C to D is unknown. So I introduce another variable and I call this x. This bit here is x. Now the energy per kilometer spent over water we call W. And then the energy over land is L. And we know that W is 1.4 times L. So put this all into formulas. Let me write down x again. So x was this bit here. So the distance BC is x, the distance BD is 13, which then means the distance CD is 13 minus x. The distance AB, so the island was A, is 5. The distance BC is x, so then the distance the bird would be flying is this one here, which is by Pythagoras, x squared plus 25, and then the square root of that. So that is this bit. Okay. Now the total energy consists of the two energies of the two paths. So we have the energy W times the distance along this path here. So let me write down this again, it's got lost. And then it is the energy L times this distance, 13 minus x, here. So that is the flight path of the bird, down here to point C and over there. The total energy is this, but now we know that W is 1.4 times L. So we can simplify the energy function as follows. So then we get energy is W is 1.4 times L square root of x squared plus 25 plus L times 13 minus x, and then we can factor out an L, and we get 1.4 square root of x squared plus 25 plus 13 minus x, and all this times L. So we don't know what L is, but we will see we don't even need to know what L is to optimize this problem. So here's this formula again. E of x is 1.4 x squared plus 25 plus 13 minus x times L. And so we see this as a function of one variable, because we assume L is given. We don't have a value for L, but still I assume L is given. We can apply our max and min methods. Let's look at the domain first. So the domain is values for x which I can possibly use. To find the domain I have to flip back to the picture. So here was x, okay. Now if x is 0, this corresponds to the point B, and x is equal to 13 corresponds to the point D. But having x negative would be somewhere out here. So like minus x, which doesn't make sense. This would kind of unnecessarily extend the flight of the bird. So it doesn't make sense to look at x negative. And it also doesn't make sense to look at x to be further away than the nest, because then the bird has to travel back. So the domain is between 0 and 13. So we have a closed interval and we have a continuous function, so we can use the closed interval method to find the maximum, or in this case, the minimum. For the closed interval method, we need to find the critical points. So we differentiate the function e. So I do a long bracket, and then I have to 1.4 times the derivative of the square root, which is 1 over 2 times square root x squared plus 25. And then I get by the chain rule an inner derivative, which is 2x. Okay. Then the 13 is a constant, so the derivative is 0. And then x has a derivative minus 1. I keep L as a constant factor here. So now I can cancel the 2's. So then this equals 1.4x divided by the root thingy, x squared plus 25 minus 1, all in bracket times L. Now critical points satisfy e prime is equal to 0, and so this is 0 when the bracket is 0, meaning 1.4x divided by the square root, x squared plus 25, is equal to 1. So then I multiply the whole thing with the square root term, and I write 1.4 as a ratio, which is 7/5. So then we get 7/5 x is equal to the square root of x squared plus 25. Now I do the 7/5 thing because the algebra becomes a little bit easier if I do it this way. So I square the equation, and then I get 49 divided by 25 x squared equals x squared plus 25. Then I bring the x squares on the same side. So 1x squared is the same as 25 divided by 25. And so I get 49 minus 25, which is 24. So I get 24 over 25 x squared equals 25. And then I can solve this for x squared. Then I get x squared is 25 squared divided by 24. Then I do the square root and I get x is equal to plus or minus 25 divided by root of 24. Now we notice that one of the points is not in the domain, right? The negative point is not in the domain, because we said it doesn't make sense to have a negative x value. So the negative term is excluded. We only worry about the positive term, which is 25 divided by root of 24. So here I wrote this term again. So we have a domain from 0 to 13, and we have a critical point 25 divided by root of 24. And now we use a closed interval method. which means we need to evaluate the function on the boundary points and on the critical points. So e at 0 is equal to 1.4 root of 25, which is 5 of course, plus 13 minus 0 times L. And then this equals, if you figure this out, this is 20 times L. At the critical point, 25 divided by root of 24, we get this is 1.4 root of 25 square divided by 24 plus 25, and then plus 13 minus 25 over root 24, and this times L. And so if you figure this out, then this is about 15.0 times L. And then finally, the last point is the boundary point 13. So then this is 1.4 times 169 plus 25 plus 13 minus 13 times L. So if you figure all this out, you get about 19.5 times L. So the minimum is clearly at 15, right? We are looking at the minimum, so here is the minimum. And then this has to be the absolute minimum because we use the closed interval method. Minimum for x is equal to 25 divided by root of 24. And then if you put this in the calculator, this is about 5.1 kilometers. So it means this bit here of the graph is about 5.1 kilometer. That would be the optimal point for the bird to land, and then continue the rest towards the nest. So let me summarize what we did. So first of all, remember the saying, you draw names for max and min. So the challenge was the 4, to find a formula which depends on one variable only, and then if we have it, everything else is easy. Then we can use our max and min methods, look for critical points, use a closed boundary method, or we could use the second derivative test, the first derivative test, all that kind of stuff, which we know so well. Now I must also say reality is not as smooth as this video, so be prepared to go back and forth between the steps until everything fits together. So maybe at some point you forget to use the energy relation between water travel and land travel, so then you go back, introduce a new variable, do it again. And if you ever have the chance to fly over water or over land, then you will see the difference. Like Tolo did. Tolo? Oh, that looks really interesting. You want to fly to the island? Okay, make sure you take the shortest path.